Okay, today, this is lecture 7 part 2, more on the motion of robots and differentiation. We are going to talk about exponential functions, differentiations of the exponential functions. Okay? So, this is what we are going to talk today. Now, what do you do first? Well, remember the exponential function, if you have some addition in the exponent, you can break that exponential function down into the product of two of them. So let's take that e to the x out of the limit, because e to the x has nothing to do with limit operation, right? And if you take e to the x out, we can see what's going on more clearly. So e to the x factored out and then take out of the limit. So we need to compute this limit here. E to the x minus 1. Once again, well, I guess that we can tell that they cannot cancel delta x, but e to the delta x goes to 1 as delta x goes to 0, because e to the 0th power is equal to 1. So 1 minus 1 is equal to 0. So that's once again what we are going to have is that may converge to some finite value because 0 over 0. All right, so let's actually compute it. Okay, how? Aha. Use a backdoor. Since we are not, well, this class is not mathematics class. This is a robotics class. I'm a mathematician, so I feel like to prove that kind of things. But there is a better way, an interesting way. That's a backdoor. All right. Consider dAx over dx for general A, not the e. E to the x power, that's the exponential function we have, but general exponential power function a to the x. Okay? Why? Because Euler, that famous Euler, showed that the derivative of a to the x is identical to the original function if and only if a is equal to e, Napier's constant. So that's the only time when the derivative becomes the same as the original function. Okay? So, really? Okay. When you are told something, you just accept it for a while, for that. But you always keep the question there. Really? And how can we check this? Let's check this an engineer's way. Since we're not really convinced with the limit, let's compute the ratio of this one here for a small delta x with different a's. For small x, probably 0.05 is enough, small enough. If not, use smaller amount. But anyway, this is what's going to happen. A is equal to 2. We have blue, the original function, and dotted red line, this is ratio. Obviously, the ratio is below the original function. How about a is equal to 5? You plotted a is equal to 5 here, the original function, and the ratio. Ratio is above the function. All right, how about a is equal to e? It's right on top of it. A little bit off because this value is okay. If you make this one smaller, probably it will go right on top of each other. So when a is equal to e, the ratio is right on this. So therefore, this limit has to be 1 because the derivative has to equal to itself. So this has to be 1. Okay, but where we use Napier's constant e, that's 2.71828 blah blah blah. I cannot remember any more than this 5 or 6 digits, but that's the number. why this number is so special? What's so special about that number? And of course, this number is defined by this one here, but it has not much of interesting. But the most interesting thing is that if A is equal to E, once again, the derivative is itself. And E, character E, was used by Euler for the Napier's constant. Before Euler, NA or NA, and those are used. But because of this definition, there is a very interesting formula. I can show you. Interesting approximation. Well, not really limiting, taking the limit. So this is an approximation. But if you look at this one here, and 3 to the second power to the 85 power. That's a big number, right? 2 to the 85 power is a large number, and 3 to that large number is a really large number. So this is really close to this constant, Napier's constant E. But do you know what's interesting about this expression here? Aha, some of you have already noticed. Well, 1, 2, 3, 4, 5, 6, 7, 8, and 9. How about that? Each number 1 through 9 appears once in every one of them. Right? This type of number is called a pan-digit number. Pan-digit formula. And this one is correct up to 18 times 10 to the 24 digits. 10 to the 24 digits. That's a large number. And this one was found by Richard Sebi in 2004, not so long time ago. 16 years ago. Well, since I'm recording this in 2020. And source is this one here. If you're interested in, take a look at it. Well, once again, the limit. So we have done polynomials, rational functions, sines and cosines, and exponential functions. Then you ask, oh boy, do we compute the limit all the time? My answer, no, definitely no. We are not mathematicians. We are engineers. So you ask again, then what we do? My second answer, since we are engineers, we compile a list of derivatives and rules for differentiation and simply use the compiled table. That's it. Well, rules. There are so many nice rules you can use, tools as a tools, and to compute the derivatives of complicated functions. So I put them together. Here we go. This is the derivative, table of derivatives. X to the nth power n times x to the n minus 1. I use that for the x to the second power and to 2x, right? That's the one we've been using. So sine, cosine, tangent, we have computed that. Exponential, computed that. From here on, I have not computed, but you can do this. Well, actually, the fourth one, ln x, 1 over x, I will show that along the way of explaining one of the rules. But anyway, sine, arcsine, arccosine, arctangent, those functions, that's done. So, I'm not saying you prove them, but use them. Since they are so useful and important, we will prove some of them in a homework. Aha, too bad. In the homework, you have to prove some of them. Okay. Oop. This is a list of rules. The first one is called the linearity. You don't know how great this tool is until you really find out non-linearity, not linearity. Well, linearity, what it does is very simple. If you have a linear operation, this is a linear operation. Okay, if you have a linear operation, then if you have summation, you can break that down. And if you have constants, you can take outside. So this is the typical divide and conquer. You can do that. Even if you have a very complex function here, if you can make it as a sum, you can break down. That's what the linearity, good part about the linearity. Super good. Okay, then the next one is product. When you differentiate the product, you get this one here. Third one is chain rule, where you have dx over, df of gx over dx. So you can differentiate this function of function in two steps. First, you differentiate dfg in terms of g. Then differentiate g in terms of x. I'll give you an example later. And fraction, this one here, is pretty much the application of b product. And modified exponential and modified trig functions. Well, either the ax, a comes out, omega comes out, blah, blah, blah. Okay, chain rule. This sometimes is called the change of variable. Here, the variable for the differentiation is x. Here, the variable for the differentiation is g, not x, right? So that's change of variable. But what is the catch here? The catch, the first term on the right-hand side. Why is the catch? Function gx is changed to variable g. It was originally a function of x. But here, in the first derivative here, g is treated just as a variable. Just a variable. So therefore, this is a regular, simple differentiation. Not the differentiating in terms of function. You are differentiating in terms of a variable g. That is the important part. Okay? A regular differentiation. Okay? An example here, d dx cosine e to the ax. So this is a typical situation where functions of function. So let e to the x to be gx. So this is a cosine of gx, right? So we differentiate that. So how we do? This one here is d cosine g over dg and d e to the d dx because this is gx. Okay? So that's cosine becomes minus sine. And this one here is a times e to the. And g, you plug back into that, and then you get this one here. That's easy, right? That's how convenient this rule is. Okay, repeat of chain rule. I would like to give you interesting fact that this chain rule can be repeated again and again. Suppose you have a function of a function of a function. Okay, function of x is u, function of u is g, function of g is f. So, not double, but triple. In this case, if you apply chain rule, this becomes dfg, dg, dgu, gu, and this one here. So, it's like repeating many times. So you look like chain, don't you think? That's why this is called a chain rule. You can do this as many times as you like. Okay, useful but not official rule here. This one is so useful, but it's not really an official rule. But you can use that. dy dx is equal to 1 over dx dy. Okay, this is a ratio, but when you take the limit of delta something goes to 0, then that becomes just a single function. So it's more than just a ratio. So therefore, this one is not equal to 1 over this. But formally, you can do that. And the example is this one here, ln x. Okay. To find the derivative of this one here, we know that that's 1 over x. But let's prove that. Okay. From this one, x is equal to e to the y, right? So you can differentiate x by y, and that's e to the y, so it doesn't change. That's e to the y. exponential function. All right? So, dy dx is 1 over this one here is 1 over e to the yth power, and which is x. So that's 1 over x. How about that? Useful, don't you think? Well, which rule to apply to your current problem? You just develop the sense to it. So if you solve enough number of problems, you kind of feel what to do, which rule to apply to your problem. So solve as many problems as possible. Linearity is this one here, as I told you, but I'd like to introduce the word law of superposition. Superpose. Law of superposition. This one here is called the linear combination. Oop. Wait a minute. Linear combination. So law of superposition is that if you have a linear combination in variable, then you can replace that with linear combination of resulting function if this operation is linear combination. And this is called the law of superposition. And this is exactly what we do, right? When we have divide and conquer. Instead of differentiating this whole thing, you're differentiating each small thing and add them together. It will give you the answer. So you can tell how convenient this one is. All right. Higher order derivatives. The reason why we have given the name derivative for the result of differentiation is actually this one here. We would like to take the derivative differentiate one more time. So those are called the higher order derivatives. Second order derivative, you have dx squared, d squared effect, which is nothing but the differentiating the derivative one more time. And so the example we repeatedly use in this course is that from position and take derivative differentiation and speed, then differentiate again to get the acceleration. For our robotic engineers, the position is actually an angle. Here, the speed is angular speed, and acceleration is angular acceleration, theta double dot. So that's what we want to do. We will do many times. Of course, we will do the other way around as well, right? But that's a future story. So let's compute the second derivative of sine. That's the differentiation of the first derivative. The first derivative was cosine. So if you differentiate cosine, you get negative sine. That's what. So you apply just differentiation again and again. So I guess it's easy. Cosine theta, the same thing here. Here, this becomes minus sine theta. So this minus sine theta differentiated minus cosine theta. Nth order derivative, you just repeat that. That's all. Nothing more. From the above example, we have a very interesting thing, and which normally will not be introduced until the second year in university. But I'd like to introduce it here because robotics engineers do use that so often. This is one of the best tools exist. So that's a coffee break. Well, let's take a look at this one again and again. This second derivative of sine is negative sine. Second derivative of cosine is negative cosine. So therefore, if I change that. Both of them satisfies this type of equation. If you differentiate twice, then you get the negative of itself. Or you can move this one to the left-hand side. You get, if you add the second derivative to itself, that becomes 0. And this is the type of equation I wanted to introduce. This type of equation is called a differential equation, DE. Differential equation. And this thing, we use this all the time. Like, if you remember Dr. Yamato's equation of motion, you have the second derivative and derivative, etc. So those are called the differential equation. We even abbreviate to DE because we use this one so often. You don't want to write down differential equations all the time. So we just call DE. That's it. Like you can call me Dr. T. Okay? That's DE. Do we know another function satisfying this equation? Do we know? Well, yes and no. It's tricky. A little tricky. Try this one here. E to the jx. Wow. E to the ax we know. And for that a constant, we use j. What's going to happen? Second derivative is a derivative of the derivative. I mean differentiation of the derivative. If you differentiate this one here, you got j here. Right? So if you differentiate one more time, you get j squared. That's negative 1. Aha! Second derivative is a negative of itself. So this one also satisfies this differential equation. So you would ask, so what? Aha! This is something we can use to prove Euler's identity. Euler's identity was, I told you, I guess I introduced that a few lectures back. And that is one of the most beautiful formula in mathematics. That can be shown from this fact that either jx and other functions, sines and cosines, satisfy exactly the same differential equation. Well, not now, but I will show you that later. Okay? And instead, I'm going to talk about the importance of the second order derivative. Second order derivative appears in many different places. Whenever you are talking about something moving, what is it? Of course, Newton's law. F is equal to ma. A is x double dot. F, m, a, x are force, mass, acceleration, and position. So the second derivative of the position appears, right? So Newton's law is written in terms of the second derivative of the position. Well, for the rotational thing, that the torque, tau, is equal to the momentum inertia times the angular acceleration here. So this is a linear motion. This is a rotational motion. So incidentally, what does a motor generate? We have done this before, right? What does motor generate? Wrong answers. It generates rotation. It generates rotational speed. Actually, the motor generates torque, right? The force for the rotational motion. And that torque will generate angular acceleration according to this one here. So not the rotational speed, not the rotation, but angular acceleration is what motor generates according to the Newton's law. So you are talking about one motor, one Newton's law. So for, well, up to now, I believe that Newton's law is just a mathematical formula for you. But for the robot engineers, Newton's law is nothing but a motor. one motor, 1 Newton's law. That nice? Okay, with that in mind, let's go back to the robokick. We had this one here, and that looks like this one here, and speed was computed, and looks like that. Well, this is trapezoid. And if I compute the second derivative, that becomes 45i, 0, 45i. I mean 45, 0, minus 45. So the torque is I times second derivative, which is this. So that's that. Is that beautiful? Required motor torque is plus minus 45i only. Right? Plus and minus 45i only. So it is easy to control. Okay? So that's why this here, the set of those piecewise functions are used quite often. All right? So this is actually the end of this lecture here. And next time we'll go into the other direction, not quite. And we will talk about one special derivative next time.